All right, y'all. Today I want to talk about the calculus concept of implicit differentiation. Now we know from the word differentiation, we're talking about derivative of some kind. But implicit differentiation, well, let me talk about this second bullet point here before I talk about the first one. Because the first one is the methodology. The second one is the why, which is most important. So basically, implicit differentiation is a method of differentiation that allows you to find the derivative of functions that define implicit relationships between or implicit relationship between x and y. Now, what in the world does that mean? What is an implicit relationship between x and y? Now, what we're used to finding the derivative of up to this point is equations where there is an explicit relationship between x and y, like y is explicit. Well, let me just write it. So for example, you have these two equations here. In this first one, this is an explicit relationship between x and y. In other words, y is clearly in, when something is explicit, that means it's obvious. When something is implicit, that means it's kind of like implied. It may not necessarily be as obvious, but it's implied. Um, But in this first equation here, y is clearly defined in terms of x. So you see the relationship. Y is actually 2x plus 1. Here, there's an implied relationship between x and y, but it's not nearly as explicit. You see you have x and y on each side of the equation, so it's not as clear. We can find this derivative pretty easily because all you do is you will say, like, for example, y prime or dy dx equals, and then you take the derivative of this side. Um, but here, it's not quite like that. Now, you could try to solve this for y here, but it gets really, really messy, because you move this x cubed over here, and then, but you still got the y right there. So how are you going to move that y over? And then if you try to move it anyway, so you kind of, hopefully you see what I'm saying. So this is what implicit differentiation, this is the type of equation that implicit differentiation allows us to differentiate. Now, the way we do it is this first bullet point. We differentiate both sides of the equation, and then we solve for y prime. So we'll differentiate this side, we'll differentiate this side, and then we will solve for y prime or solve for dy dx, whatever the problem is asking us to do. Same thing. All right, so let's actually do that. So I'm going to erase this first one here. Hold on, let me do it this way. Sometimes this thing will erase more than I want it to. So we're going to erase that. All right. So now let's do implicit differentiation. Let's use implicit differentiation rather to solve this. All right, so the derivative of x cubed is going to be 3x squared plus. Now, if we differentiate y cubed, we have to use the chain rule. Basically, we know that um y is a function of x. So we're going to take the derivative of the outside, which is going to be a derivative of like this. So that's going to be 3y squared. And then that's going to be times the derivative of y, which y is a function of x. So that's just going to be times y prime. Okay. All right. So now that's going to be equal to the derivative of this other side. So we're going to do the first times the derivative of the second plus the second times the derivative of the first. The derivative of 6x is just 6. It's going to be 6y. All right, so let's combine these a bit. So you have 3x squared plus 3y squared y prime is equal to 6xy prime plus 6y. Okay. All right. So let's keep on going, and we're going to move the y prime stuff on one side and move the stuff that doesn't have a y prime on the other side. So let's do that. I'm going to do that in one step. So just follow what I'm doing. So you got 3y squared y prime minus 6xy prime is going to be equal to 6y minus 3x squared. Okay. Now we can factor out a y prime on this side. So that's going to be 3y squared minus 6x equals 6y minus 3x squared. Oops, I didn't need to draw that other parenthesis there. Is that how you say that? Parenthesis. All right, and then finally our answer, we're going to divide both sides by 3y squared minus 6x. 3y squared minus 6x. So you're going to have y prime equals 6y squared minus 3x over 3y squared minus 6x. Now, if you notice, all of these have a factor of 3 in there. So we can divide both sides, both the top and the bottom by 3. So that makes y prime equal to, that's going to be, let's see, divided by 3, that's going to be 2y squared minus x over y squared minus 2. Okay. All right, so that's that. Oops, I didn't mean to do that. Sorry about that. Now let me go back and correct here because I see that I made a little mistake here. So I'm gonna go ahead and correct this in real time. You know, math tutors do make mistakes sometimes. So let me go back because what happens is I kind of added a squared term here and it wasn't squared. 6y was just it was just 6y wasn't 6y squared. So let's see if we can erase that without erasing extra stuff. So that was 6y minus 3x squared. And then we divided both sides by, let me see. So we had y prime 3y squared minus 6x, 3y squared minus 6x, 3y squared. Okay. All right. So now let's try that again. So y prime. So when we divide the bottom and the top by 3, that's going to be 2y minus x. Okay. Let me see. Actually, x squared. That was the squared term there. Okay. 2y minus x squared over, that's going to be y squared minus 2x. Okay. Now, keep in mind that because I actually solved this using some notes where I solved it before. And the answer that I have is actually almost like the negative, like as if I multiply the top and the bottom by a -1. And that's okay. It's the same thing. Okay. All right. So that is that. Now, let us solve another one just to get a little extra practice in. Go ahead and erase all this stuff here. If you need to copy it down, you know, thanks to modern technology, you can go back and rewind and then get it again. All right, so let's see the other example I wanted to do. Okay, yeah. So we have this function here, 8x squared plus y squared equals 10, and we want to find dy dx. Remember, dy dx is the same as y prime. All right, so we're going to differentiate both sides, just like we did last time. It's going to be 16x plus, chain rule for this, so that's going to be 2y times dy dx. Okay, because you took the derivative of the outside function, then you took the derivative of the inside. excuse me. So that's going to be equal to 10. Now all we need to do is solve for dy dx. So we're going to subtract 16x from both sides. Okay. So you have 2y dy dx equals 10. Oh, I was about to make a big mistake. Do you see what I was about to do? I didn't finish differentiating. Implicit differentiation requires that we differentiate both sides. So before I subtracted that, I needed to differentiate 10, and the derivative of 10 is 0. And then we subtract 16x. So now you have 2y dy dx equals negative 16. Okay. Now, we're going to divide both sides by 2y, and we're almost there. Put that x there. So our final answer, dy dx equals negative 16x over 2y. It's not our final answer because we can take out a factor or 2 from the top and the bottom. So dy dx is equal to negative 8x over y, and you are done. That, in a nutshell, is implicit differentiation. There are probably examples that'll be more involved, like with trig functions and whatnot, but the solution is, I mean, the way it works is exactly the same. So hopefully this helps. Make sure you like and share this, subscribe to my Math Swap tutoring channel. I'm mainly doing calculus videos now, and then sometimes algebra 1, but I do other ones as well, especially as the need arises. But yeah, and make sure you sign up for tutoring too. We got 6 total tutors on the team, so we got plenty of people who can help. So don't try to figure it out on your own. Get some help, okay? All right.